This video is going to work best if you're able to interact and think about it as different questions are posed. It's going to work even better if you're able to talk with classmates or someone else to be able to compare your ideas. You can simply follow along, but you'll get more out of it if you put more into it. Within this video, we're going to look at some ideas from the start of Chapter 2, which discusses the discovery of atomic structure. It's not intended to be an overview of all that material, but to illustrate how these ideas will show up on our tests. We want to know things like who was the scientist, what was the experiment, and why it was significant, to have an understanding of how the experiment works, and then specifically to distinguish between what was observed and what was inferred in the experiment. First of all, the scientists and what the experiments associated with them, we want to be aware of three different scientists, Thomson, Millikan, and Rutherford. Looking at Thomson, his experiment involved the deflection of cathode rays, and with this deflection of cathode rays, which we now call electrons in electric and magnetic fields, he was able to measure their ratio of their charge to their mass. That's what the QM ratio represents. This led to him proposing a plum pudding model of the atom. Robert Millikan's associated with the oil drop experiment, in which he manipulated the rise and fall of oil droplets that had become charged, and in the applied magnetic field he was able to suspend them. This led to measuring the charge of the electron and then determining the mass of the electron. With Rutherford, we have two experiments that we want to be familiar with. The first is when he directed radioactive emissions through an electric field and deflected them. This led to the characterization of the nuclear radiation as alpha, beta, and gamma emissions. Rutherford's second experiment we want to be familiar with is his gold foil experiment, in which he measured the scattering of alpha particles that had struck a thin gold foil, and it led to his proposed nuclear model of the atom. The intention here is not to look very deeply at all of these experiments, but instead to consider how they can show up on midterm exams. So consider this one. The question is, what do Thomson's investigation of cathode rays, Millikan's oil drop experiment, and Rutherford's investigation of alpha, beta, and gamma radiation have in common? So in order to answer this, we need to know what did each of the experiments include. In order to make a comparison, if we want to compare and contrast them, we need to know what they were involved with. And it looks like that we have a range of choices here. Some of them are talking about the parts of the experiment. It looks like response C is what was being observed, and response D is what was being investigated. Well, in terms of J.J. Thomson's deflection of cathode rays experiment, if we look at these, does it include electrically charged plates? Yes, it does, but it does not include radioactive sources. Millikan's experiment, in which we had our oil drops falling through the chamber, did they include electrically charged plates? Yes, that's what caused the droplets to be suspended. How about the investigation by Rutherford of nuclear radiation? Yes, once again, they were being sent through electrically charged plates, and that caused their deflection. So clearly, the best answer here is all three of these used electrically charged plates. If we look a little bit more closely at the choices, let's be clear. It says in C, direct observation of subatomic particles. All three of these experiments are involving, in some way, subatomic particles, but we're not directly observing them in, let's say, the oil drop experiment. Instead, we're seeing how an oil drop can be suspended. We're not actually seeing the electron. So we want to be careful because this is using the language of observation versus inference, which is another one of our learning objectives here. So let's look more closely at Millikan's oil drop experiment. So the idea here, once again, is we have a fine mist of oil that falls into the bottom chamber. An X-ray source is going to cause them to be acquire a negative charge. Millikan's able to observe the droplets as they fall. through the bottom part of the chamber. And again, they're dropping because due to the force of gravity. Because they require a negative charge, he's able to turn on an electric field and catch a particular droplet and suspend it. And at that point, he knows that the force of gravity and the force of the applied electric field are the same. So the particles are becoming negative because the X-rays, with their ionizing radiation, are transferring electrons from the air in the chamber to the particles. They're becoming negative. If we look within our picture, it shows that the top plate is positive, the bottom is negative, so that's why with opposites attract, it can be held within there. And the question is, well, what if the opposite occurred? What if the electrons were being transferred instead from the oil to the air? Could it still work? Well, in this case, the droplets would be becoming positively charged. So if we look within the choices, would it work? It would work, no modification necessary, choice A. No, I don't think that's true. I think that you couldn't suspend them if the particles had acquired a different charge. Okay? Looks like the best choice would be D. It would work, but you would need to switch the plates. You'd need to make the top one negative and the bottom one positive if the particles were now positively charged. But remember, they're negatively charged, and that's why we're able to suspend them with that initial setup. So clearly within this question, in order to answer it, you need to have some insight both in terms of the setup and how it worked. Here's another one on Millikan's oil drop. It's asking us to distinguish between an inference and an observation within the experiment. So in order to answer this one, we need to know what the difference is between an inference and an observation. An observation, well, observations are what our senses tell us, what we might see, smell, or read from an instrument. Inference, those are the conclusions that we reach based on our evidence and our reasoning. So we look at our choices right here. Let's say choice D, they fall at different speeds. Well, that is something he could directly observe. They fall downward in the absence of an electric field. Yep, that's again something that Millikan could see. The A, they may be suspended in an electric field. That's another observation. He turns on the electric field and he's able to see that they're suspended. They acquire a negative charge. That is the inference. He is inferring they acquire a negative charge because he observes that when he turns on an electric field, he's able to suspend the particles. So we want to really know the experiments well enough so we can distinguish, again, between inferences and observations. Not just for the oil drop experiment, but for also the work by J.J. Thomson and Rutherford. Here's another application where we look more closely at Millikan's experiment and his data analysis. It says, a chemist is seeking to reproduce Millikan's oil drop experiment. Data for 4 trials are shown as the filled circles, and there's new trials, which are the open circles. Which of those would be consistent and support Millikan's findings? Now, in order to answer this one, we have to know how he analyzed his data. So what Millikan did is he had many different trials, shown here sorted by the amount of charge on the particular droplets, and he found that when he grouped them this way, there was a sort of a staircase as the incremental change from one group to the next seemed about the same difference time and again. He took this difference to be the charge on the electron itself, and so what was happening is different numbers of electrons were on each of the different droplets. So as long as we had the staircase effect, he was able to say that is the charge for the electron. So if we look back within the proposed data right here, point 1, is it possible to have less charge than the other droplets that were shown? Yeah, that's okay, as long as it keeps that same incremental pattern. In droplet 3, could you have more charge? Yep, once again, as long as it's keeping that same incremental step size. The one that would be contradictory would be value 2. That's somehow in between 2 of the drops. So if that one's applicable, then the charge of the electron is actually smaller than what the other data set is proposing. So both 1 and 3 would be consistent because they're exhibiting the same step size, so the same fundamental amount of charge that's found from droplet to droplet. Here's another one that's related to these experiments. It says different particles are sent through a magnetic field to deflect their path. Which of these has a trajectory that matches that most closely of a helium-4 2+ cation? So take a second, pause this one. What experiment does this one relate to? And what do you think your answer is? In terms of what experiment does it match up with? Well, this idea of being able to deflect particles based on their charge and their mass. It shows up in two different experiments. It showed up in the cathode ray experiment where the electrons were being deflected, and also in Rutherford's experiment when he had his investigation of radioactive emissions. In both cases, we saw a deflection based on the charge and the mass. That's how J.J. Thomson ended up determining the charge to mass ratio for the electron, and how we see that different alpha and beta particles are deflected differently and in different directions because they have different charges and different charge to mass ratios. In both cases, it's this charge to mass ratio that affects the path. A large charge to mass ratio results in a larger deflection. Now this could be due because maybe the charge is large or because the mass is small. In either case, it's the charge to mass ratio that affects a particular path. So if we look back within the question right here, helium-4, the mass is 4 and the charge is 2+. And there's my dog talking about, who knows what he's talking about. So within here, I'd like to see something else that has that same charge to mass ratio. It doesn't have to be a mass of 4 and a charge of +2, but we want to see the ratio the same. And that's what we see with a hydrogen 2+ cation. The charge is +1, the mass is 2. For the previous example, it was 2 and 4, so they're in the same ratio. They would have a very similar trajectory through that field. The topics that we looked at here were involving the atomic structure. When I say various ideas were included in this video, I was really trying to illustrate how they can show up in different ways on the test. In terms of mastering the content, I think you will have seen that you really need to know each of the experiments, not at a superficial level, but with a deeper level if you want to be able to compare experiments, consider aspects of data analysis. These questions, as shown within this video, are not going to be identical to those that are on your test, but I've tried to illustrate once again that you really have to have a good understanding of the experiments if you want to try to reach the level that we're striving for. If you made mistakes or some of these experiments were unclear, excellent. Now's the time to make those mistakes. Document your errors, figure out your weaknesses, and strive for mastery.